This is the last video we devote to basic voltage measurements with high bandwidth oscilloscopes. Some of these instruments have an interesting feature. We can change their input impedance between two possible values. The first one is the usual reference impedance in microwave engineering, 50 ohm. The second one is the impedance typically found in low-frequency electronics, 1 megaohm. Let us check the behavior of our oscilloscopes when we choose this 1 megaohm impedance. We have two oscilloscopes with variable input impedance, the Yokogawa DL6154 and the Tektronix TDS3052. We can find in the front panel the equivalent model of the oscilloscopes when we choose the 1 megaohm impedance. This is an admittance model consisting in a resistor connected in parallel to a capacitor. Let us assume that I connect the oscilloscope to a power generator providing a 50 MHz signal with a power of 10 dBm. I want to predict the peak-to-peak voltage that I would measure. We did something similar in a previous video with a 50 ohm impedance. We found that the simplest model can be used to accurately predict the voltages, provided that we work at low frequencies. We demonstrated this by doing measurements at 50 MHz. Okay, I don't want to complicate my life. I just change the oscilloscope impedance to 1 megaohm, choose 50 MHz again, and try to predict the peak-to-peak voltage using the simplest model, as we did before. I should better use the parallel admittance model since I have the oscilloscope parallel resistance and capacitance. I know that my generator provides 10 dBm and I know that the input resistance is 1 megaohm. I calculate the peak-to-peak voltage and obtain 202.84 volts. Not bad for a power of 10 milliwatts, isn't it? Let us check this. We start with Tektronix. I go to the quick menu, choose 1 megaohm, menu off, and I got 4 volts. Oof, a bit lower than I expected. Let us see what we measure with the other oscilloscope. Maybe this one is not working. I press the channel button, go to coupling, and choose DC. Nice. It is even lower, around 3.7 volts. Something happens. Yes, you probably got it. Of course you got it because you have studied some transmission line theory. Of course, the problem is that we cannot ignore the reflections. Maybe this helps to clarify the situation. We know that the power delivered to the oscilloscope depends on the reflection coefficients. If we just take an ideal oscilloscope with no parasitic capacitance, just a 1 megaohm input impedance, we got a nice reflection coefficient of 4 nines. Of course, the resulting power delivered to the oscilloscope is less than 2% of the incident power. The numbers might be surprising for you because you have studied the relevant formulae in a course on high-frequency electronics, but these equations are perfectly correct even at low frequencies. Your frequency is low, but this doesn't matter. You have an enormous mismatch. On the other hand, your detector, I mean the oscilloscope, measures voltage, and it is located just at the place in which the reflected voltage and the incident one are in phase. This leads to a total voltage that is around 2 times the incident one, so you are indeed taking benefit of this reflection. Actually, a number of sensitive detectors use this effect. But my oscilloscope admittance also has a capacitance, and I want to know what should be the true value of the peak-to-peak voltage. To find out this, you need the input impedance, which can be obtained by two different ways. First, you can use the admittance model of the manufacturer, or you can measure the impedance with the network analyzer. Let us choose this option first. It is time to find out another surprise. I have measured the reflection coefficient of my oscilloscopes and get the results shown here. The marker is located at 50 MHz and we can read directly the impedances we are looking for. Now I write a small script in MATLAB to make a cross-check between the measurements of my network analyzer and the model given by the manufacturer. And this is the result we finally obtained. We got a good agreement in the capacitance, but very poor one in the resistance. We might wonder why and if this is important for the final estimation of the voltages. We can immediately clarify the first question. You can imagine what happens. Your resistor is huge, 1 megaohm, and is in parallel with a capacitor which provides a parallel susceptance that is much larger than the inverse of this resistance. In other words, the network analyzer measures only the capacitance. It is good doing this, but we cannot ask it to give us an accurate estimation of the resistance. Anyway, let us estimate the voltage with this and see what happens. And these are the final results. Both estimations are quite reasonable and it is unclear which option is better. It depends on the value of the impedance we measure. We see that the poor estimation of the parallel resistance from the measurements done with the network analyzer does not make any strong influence on the final values of the voltages. Consistent values are actually obtained since the slight underestimation of the reflection coefficient magnitude is partially compensated by the underestimation of the oscilloscope conductance.